This podcast is brought to you by HEC Paris.
Thanks, Laurent. Thanks for the opportunity. It's a pleasure to be here. The paper I'm going to present is joint work with Rob Stambaugh. And in one sentence, we ask, why is the active asset management industry so large when its track record is so poor? That's what we try to answer here. So let me begin with some facts. If you look at the track record of active equity mutual funds in the United States, you aggregate all of them into a portfolio, you see that on average their alpha has been negative over a long period of time. And this evidence is on the margin of significance. So for example, depending on which benchmark you use to benchmark these mutual funds, the t-statistic could be minus 1.5, minus 2.5. It's in the neighborhood of minus 2. So faced with this poor track record in general, it may seem a little surprising that active management remains so popular. For example, about 87% of mutual fund assets in the United States are actively managed. So indexing has grown, but it's still a relatively small part of total asset management. So is there a puzzle? Why don't we all index? Okay. Now, people have asked this question, and as far as I'm concerned, there isn't really a coherent explanation out there. Perhaps one explanation people have provided is that, well, people are just silly. They don't understand this, and retail investors pour money into these active funds, and they just keep making a mistake. So they shouldn't be doing that. We have an explanation in this paper that does not require anybody to be silly. So we have an explanation in which everybody is perfectly rational, and the reason why the industry is so big is related to decreasing returns to scale in the active management industry. Okay? So let me tell you about that. So here's the explanation that we propose in this paper. We argue that as the industry gets bigger, it becomes more difficult for any given money manager to outperform. And you're going to see this relation one way or another throughout the presentation, so I might as well talk about it a little. Alpha T denotes the alpha, so think of it as Jensen's alpha of the aggregate mutual fund, active mutual fund industry at time T. And we model it, and this is an assumption, this is the biggest assumption in the paper. We model it as a linear function of S over W, which is the fraction of investors' wealth that is invested in active management. So to be more precise, W here is the total wealth of investors in active funds. S is the size of the active management industry, so S over W is the fraction of wealth that investors invest actively. You'll see S over W all over the place. Now, we believe that it makes sense for B to be greater than 0. We believe that as the industry gets bigger, as more money chases mispricing is harder to come by, and so any given manager will find it harder to outperform his or her benchmark. Okay? So that's the starting point. Now, this alone helps you understand why the active management industry can be big even after a negative track record. What happens if you observe underperformance in the world of decreasing returns to scale? Well, I will tell you later, by the way, that A and B are unknown. I don't know about you, but I don't know what A and B are. I have to learn about A and B from past data, and so I have to learn about alpha as well. Now, if I observe underperformance, I'm going to revise my beliefs about alpha, and I'm going to revise them downward. When I revise my beliefs about alpha downward, I'm going to pull some money out of active funds and put it in index funds or cash. However, and that's crucial, I'm not going to disinvest as much as I would if I knew that returns to scale were constant. So under constant returns to scale, or B equals 0, alpha is constant. Okay, and there are hundreds of performance evaluation studies that assume constant alphas. All of those studies assume constant returns to scale. Okay. In a world like that, you see negative benchmark adjusted returns. You adjust your estimate of alpha downward, and you pull money out. Okay. In this world, the same thing happens. However, you disinvest much less. Why? Because you understand that when you reduce your allocation to active management, your alpha going forward is going to improve. Okay? Because of this. If you reduce S over W with B greater than 0, your alpha going forward is going to increase. So yes, you will reduce your investment to active management, but not as much as you would in the world of constant returns to scale. This alone can generate, I think, the world we see around us. In particular, I'm going to show you later that when we apply our model to observed actually observed mutual fund returns, and we assume that investors S over W begins at 0.9 in 1962 when our data begins. So investors have 90% of their wealth invested actively. And then they see the actual series of mutual fund returns. Okay. Then they end up reducing their allocation down to about 0.7. So even after 4 decades of a negative track record, investors remain 70% actively invested and only 30% in other things like cash and passive funds. Okay? This would not be true if we assume constant returns to scale, which is the more traditional assumption. In fact, I will show you that in the world of constant returns to scale, the active management industry would disappear after just 7 years. 7 years of negative benchmark adjusted returns would have been enough for investors to pull all of their money out of active management. And that's not what we see around us. So that's why we kind of believe that decreasing returns to scale are important. Okay, so this is the key, and I'm going to tell you more about, I'm going to fill in the details as we go. So what we do in the paper is present this idea in the context of an equilibrium model. It's a partial equilibrium model, very much in the spirit of Burke and Green's well-known 2004 paper. In this model, we have investors who maximize utility and decide how much to invest with active managers. We have fund managers who maximize their fees and compete with each other just like investors do. And importantly, we have uncertainty about returns to scale. So these quantities A and B from the previous page are going to be unknown. We're going to learn about them, and you'll see that learning about A and B is actually very interesting. In the context of this model, we solve for 3 things. We solve for the equilibrium size of the industry, so S over W, what fraction of investors' wealth is invested in active funds. We solve for the equilibrium alpha in the industry. It's going to be positive. And we solve for fees that active managers charge. And then we take this size that we solved for earlier and we relate it to past performance. So we want to see, well, what kind of size would you expect to see in this model if you observe this or that past performance? And then finally, we analyze learning about A and B, learning about returns to scale. So that's what we do in the paper. What do we find? Let me summarize this up front so you know where I'm going. So our first result, I already talked about. Our first result is that the size of the active management industry can be large even if the track record is poor. Our second contribution is to point out that learning about returns to scale in active management is slow. And it's endogenous in a way that I'm going to explain shortly. In fact, it's so slow that you never learn the degree of returns to scale exactly in this model. You can learn for thousands of years, and you're not going to pin down A and B. Why is that? Well, here's the intuition. And it's kind of hard to deliver it without a model, but I'll try, and then you'll see the model later. So there's this interesting endogeneity in learning. What investors learn determines how much they invest, and that's present in all models. But what's interesting here is that how much investors invest determines what they learn, because the more they invest, the lower the returns that they get in the future. The less they invest, the higher the returns that they get in the future. And this looping generates, let me show you what it generates. Our investors learn about the intercept and slope from this regression here, where R denotes the benchmark adjusted return of active mutual funds, and epsilon is just the disturbance. So this is the equation that I showed you earlier, except you see that alpha is the expectation of R. Investors learn about A and B. Now, having some beliefs about A and B leads investors to choose the equilibrium value of S over W. So with some beliefs about A and B, you decide how much to invest in active management. Okay? And then once you've decided how much to invest in active management, once you've changed the right-hand side variable, so the right-hand side variable is endogenous, once you've made that decision, you're going to get another draw of returns that depends on how much you've invested. So you see how this goes back and forth. And now here's the interesting thing. The right-hand side variable here stops changing at some point. Okay? In particular, note that if the right-hand side variable stops changing, learning about A and B stops. In equilibrium, we find that at some point investors get stuck at a certain level of S over W. They're competing, so they cannot coordinate to move this. And, well, you can run this regression on however many observations you want, but if your right-hand side variable is not changing anymore, you're not going to gain any more information about A and B. Okay, so I didn't know that when we started working on this project, that this would be a feature of our simple model. We also find related to this that the size of the industry converges to its optimal level quickly when B is high. So when returns are steeply decreasing in scale, investors quickly find out how much they should invest. However, when B is low, when returns to scale are relatively flat, then it can take hundreds of years before investors figure out what the optimal size of the industry is. Okay? You can't quite see this yet intuitively, but this is one of our results that I'm going to discuss. So that's our second result about learning about A and B. And then finally, the model I'm going to discuss has some interesting features of its own. You'll see that the size of the industry, the equilibrium size of the industry, depends crucially on the degree of competition, on the degree to which managers in particular compete with each other in setting their fees. You're going to see that the equilibrium level of alpha in the model is positive. It's tiny, usually just a few basis points, but it's positive. Investors need to be induced by a positive alpha in order to be willing to invest with active managers. And this positive alpha, by the way, does not contradict the fact that the historical alpha has been negative. Because under decreasing returns to scale, historical performance does not translate into future performance. Historical underperformance doesn't imply future underperformance. All it implies is that you should invest less. If you've seen a negative alpha empirically, all you should do is invest less in active management, and you could still be expecting a positive alpha going forward. This, by the way, is different from the result in the famous Burke and Green model, where you have a zero alpha, just kind of by assumption. And then I'm going to discuss an interesting investment externality, which is a feature of our model. This will have to do with the fact that when an N+1st investor invests in active funds, they dilute the returns of all the investors who are already invested in active funds. And this will be very clear from simple closed form formulas. So this is what we find. That's the summary, really, of our results. Let me tell you briefly about the model. We have two types of agents. We have M managers of active funds. These managers have skill, so they can potentially identify mispricing. However, they have no capital, so they can't invest on their own. They need investors to give them capital, and investors cannot find the mispricing by themselves. So this is something. We're not the first to split up agents in these two ways. Now, alpha is going to be the expected benchmark adjusted return of fund I, and a little tweak, which is not crucial, but we do assume that these errors, U, have a common component in them. So even after you take out benchmark exposure, like S&P 500, all kinds of Fama French factors if you want, even after you take those out, active managers' returns will remain correlated. The reason we believe that's sensible is that if there's mispricing out there, it's likely to be found by more than one active manager. Right? Skill is the ability to identify mispricing. So if there is mispricing out there, multiple skilled managers should identify it. So active managers should have holdings that are correlated with each other, even after you adjust for any benchmark exposure. Okay? And this X denotes the common component. Now the key assumption that I already alluded to earlier is that profits to ith manager are linear in the size of the fund. Okay, so in particular, profit is equal to the size of the fund times this thing which you can think of as alpha. We're assuming for simplicity that A and B is the same for all funds. Keep things simple. There's only one A and one B for everybody. And S over W is the aggregate size of the industry. So we're not assuming in particular that there are decreasing returns to scale at the fund level. We're not saying that as the individual fund gets bigger, their alpha goes down. That is the assumption of Burke and Green. That's not where we're going. What we're assuming is that as the whole industry gets bigger, it's more difficult for any manager to find alpha. Okay. And then manager I charges a proportional fee. So the net alpha here is going to be, well, A minus B times the relative size of the industry minus the fee that's paid out. Important, A and B are unknown in this model. In the model of Burke and Green, for those of you who have seen it, A is unknown, but B in the different context is known. So one way to imagine this, A minus B times S over W relation is just this. Here I'm plotting the linear relationship. If S over W is 0, so if no money is invested in active management, then there is a positive alpha, a positive expected rate of return. And then as the industry gets bigger, the expected return gets smaller, by assumption. Now, we actually think that A is very likely to be positive. If nobody invested in active funds, if all of us switched into index funds, there wouldn't be anybody out there paying attention to potential mispricing. So the first dollar invested in active management would earn a return A. The first dollar invested in active management would be picking low-hanging fruit, so almost surely they would earn a high alpha. It could easily be in the hundreds of percent per year. But then as more and more people pursue mispricing, it's going to be harder for anybody to find. It's kind of like police and crime. If you didn't have a single policeman in the street, presumably there would be some crime, and installing the first policeman would help. And then as you install more and more police, presumably the amount of crime decreases. It's the same thing. I'm not trying to imply that active management is a crime. All right. Far from that, I'm trying to provide a justification for its existence and size. So each manager here chooses his own fee to maximize the fee revenue, and F is the discretionary part of the fee. Each investor chooses how much to invest in each of the M funds, and we're assuming for simplicity a mean variance utility function. So everything is very easy to, so it's easy to solve for. No shorting of funds. And there's the risk aversion gamma. Okay, all investors are the same, by the way, ex ante, and all funds are the same ex ante, just to keep things simple. Case one, that's very easy to solve, and that already gives some insights, is the case in which investors are risk neutral. So 0 gamma. We solve for a symmetric Nash equilibrium in which each investor takes into account what everybody else is going to do, and each manager is going to take into account what everybody else is going to do, and it's a symmetric equilibrium. In this case, you're looking at the equilibrium fee, the equilibrium alpha, and the equilibrium size of the active management industry. All funds charge the same fee. All funds earn the same alphas in equilibrium. Again, a symmetric equilibrium. If there's only one manager out there, or put differently, if money managers collude and act as a monopolist in setting their fees, then they set a substantial fee, A over 2. Oh, the tilde on A denotes the perception of A conditional on the data that everybody has seen. So money managers extract half of the total expected return earned on the first dollar invested in active management. There's an equilibrium alpha that's positive, as long as A is positive. And this is the size of the industry. Now, when M is greater than 1, all you need is 2 managers, and they will compete down their discretionary fee all the way down to 0. So they will end up charging only the fee that covers their costs in the model. You see that alpha is twice as large as it is under the case of monopoly, and the size of the industry is twice as large as it is in the monopolistic case. Essentially what happens is that when managers compete, they will compete their fee all the way down, As a result, investors will find it more rewarding to invest, and the industry will be twice as large, and their alpha will be larger because they're not paying any fees. Okay. What's interesting here is that alpha in both of these cases is decreasing in n. I can remind you that n is the number of investors in the model. When you have an infinite number of investors, n going to infinity, then alpha is always 0, kind of like in the Burke and Green model. However, when you have a finite number of investors, investors are not willing to invest so much money in funds that they would reduce their alpha all the way to 0. This is the externality that I mentioned earlier. When you have the n plus first investor coming into the active management industry, they dilute everybody else's returns. Now, when n is finite, investors internalize some of that externality, so they're not willing to dilute their returns all the way down to 0. When n is infinite, well, then they do dilute all the way down to 0. Okay? So that's risk neutrality. It already generates some early results. Risk aversion is more realistic. In this case, we, just to keep things simple and to be able to solve for a Nash equilibrium, we let the number of managers as well as the number of investors go to infinity. So you can think of the mutual fund industry. We have a lot of investors and a lot of managers. We have more managers than stocks, at least in the United States. So we solve for a symmetric Nash equilibrium among investors. And we find, and this is not terribly illuminating, but we have a closed form solution for the size of the industry. And the solution is the unique real positive solution to this particular cubic equation. Now, it just turns out this way. What matters for me is that I can quickly solve the problem. Interestingly, you can plug in, you can see that that solution, the equilibrium size of the industry, can also be written as A, the perception of A, divided by B plus gamma times sigma x squared plus sigma alpha squared. Now, this is actually intuitive. So if A is larger, if the return on the first dollar invested in active management is larger, then the industry will end up being larger as well, because it's a more profitable enterprise. If B is larger, if returns are more steeply decreasing in scale, then the industry will end up being smaller. If investors are more risk averse, well, they'll invest less in active management. And if this common component of risk that I mentioned earlier is larger, or if parameter uncertainty about alpha is larger, again, the industry will be smaller. So we have a simple characterization of the equilibrium size of the industry. Now, I want to show you how this works when investors learn about A and B in a Bayesian fashion. So investors will start with some prior beliefs about A and B, and then they will update these beliefs with data when they observe actual returns. And I'm going to consider two priors for B, because B is the crucial quantity. Prior 1, B equals 0, constant returns to scale. So if you take most of the literature on the subject, it's constant returns to scale, constant alphas, as I've mentioned, so that you can view prior 1 as the traditional perspective. Okay? Prior 2 is that B is greater than or equal to 0, but it's unknown. So returns are decreasing in scale, but we don't know how much. And that's the prior that I think, that's my prior. Okay? We're going to have just one prior for A, which I'm going to show you shortly. And we also we have to pick some other parameters. It turns out they're not important, not terribly important. So we just specify that at the beginning, say, whenever our mutual fund data begins, investors have 90% of their wealth invested in active funds. And then we'll see how far down are they going to go from 90%. We pick risk aversion of 2, we pick sigma x of 2%, but it turns out when you double or half those two numbers, nothing changes. Okay. These are the priors. Our prior for A is this. We just use one prior. If you change it a little bit, it doesn't really matter. So most of the prior mass is above 0. As I've mentioned, the first dollar invested in active management is likely to earn a positive risk-adjusted return, but we do allow A to be negative. And we have two priors for B. One, the dashed line is just a spike at 0, so that's constant returns to scale. The blue line, you see, is the prior that B is greater than 0, but I don't know how big it is. Okay. Now, look at the implied priors for alpha. That's actually quite interesting. In the case of B equals 0, our prior for alpha is invariant to S over W, right? When B is equal to 0, alpha does not depend on S over W. Whereas when B is greater than 0, the prior on alpha does depend on S over W. In particular, as investors invest more in active management, alpha gets smaller. And comparing these two graphs, you see that investors are always more pessimistic here. In the way we set it up, investors are always more pessimistic about alpha under decreasing returns to scale. We set it up like that on purpose because I'm going to show you that even though investors are always more pessimistic about alpha under prior 2, they will end up investing a lot more in active management under prior 2, despite their more pessimistic prior. So optimism is not our story here. Here's the first result. What I'm showing you is on the y-axis is the posterior distribution of the equilibrium S over W, and on the x-axis is the sample t-statistic on alpha hat. If you, as an econometrician, run a regression of all active funds on the benchmarks, you get a t-statistic on alpha hat. Conditional on that t-statistic alone, what would you expect the size of the industry to be? Well, B equals 0 prior, that's the top panel, would lead you to invest either all or nothing in active management. Essentially, whenever you see a positive t-statistic, well, bigger than 0.25, you would go all in. Whenever you see a negative t-statistic, you would invest nothing. That's how mean variance optimization works with a lot of observations. Down here, this is B greater than 0 prior to decreasing returns to scale, and you see you get a very different result. For example, even when the t-statistic is -2, which is kind of what we observe in the data, your posterior for the equilibrium S over W ranges from something like 5% or maybe 3% all the way to the 70s. In other words, it's quite conceivable, and this is the 5th through the 95th percentile. In other words, it's quite conceivable that investors could invest more than 70% of their wealth in active management, even if they observe a t-statistic of -2. Again, as I said earlier, past underperformance does not imply future underperformance. Past underperformance implies you will reduce your allocation to active management, and your alpha going forward will improve as a result. So this is what we find. In other words, the active industry could be quite large, even if the t-statistic is -2. Next, we show that the active management industry should be quite large, given the actual series of returns that we have observed. What I'm showing you on the y-axis is the equilibrium S over W in our model as a function of time. We start in 1962 with the priors I showed you, and the blue line is decreasing returns to scale, the prior to. The dashed line corresponds to the investment strategy of investors with constant returns to scale, the more traditional perspective. You see the dashed line bounces from 1 down to 0, back to 1, and then after 7 years, investors have already learned enough about the negative performance of the industry that they no longer invest anything in active funds. Well, that's not the world we live in. The world we live in actually looks a lot more like the blue line, which is what you obtain under prior to. So investors started investing 90% in active management. Then they reduced their allocation quickly when they discovered that the initial returns were negative. And then they've been reducing their allocation, but very slowly. And they end up with about 70% invested in active management as of today. Here you see that learning about A and B is very interesting. On the left is prior 1, B equals 0, and learning is not interesting. Learning works, standard square root of t learning. But under decreasing returns to scale, B greater than 0, learning is just very unusual. For both A and B, you're looking at the drop in the posterior standard deviation of A and B in these two panels, and you see that you learn much more in the first 3 or 4 years than you learn in the subsequent 50 years. Essentially, in the first 3 or 4 years, you figure out roughly where you should be, what your S over W ought to be, and while your S over W is changing, you learn a lot about A and B. That's like the intercept and slope from the regression of returns on S over W. While the right-hand side variable is changing, you're learning a lot about the slope. and the intercept. But once you settle on a particular allocation, your right-hand side variable stops changing, and then your posterior standard deviation stays basically flat. Okay, there is a mild decline, but it's so mild that you can't even see it. So that's the slow endogenous learning. And I don't have much time left, so why don't I just show you one last figure. So these are results based on the actual mutual fund series, some selected results in the paper. First of all, here in the top two panels, I'm plotting the posterior distributions of A and B that our investors have after updating their priors with the actual mutual fund series. And you see that their posterior distributions remain quite wide even after 40 years. So even though they're learning about A and B, you know, the distribution is kind of narrowing. It's narrowing very slowly. It's very hard to learn about returns to scale. That's one of our key conclusions. It's easy to learn about alpha. It's just hard to learn about A and B. And finally, this is the learning path of our investors. They start at 0.9. I'm plotting return against S over W, benchmark adjusted return against S over W. Our investors start at 0.9, then they quickly decide, oh, they should invest a lot less than 0.9, something like 0.8 or 0.7. Then they keep searching for a decade, about a decade, maybe 15 years. They keep looking for the right allocation. And then they're happy with 0.7. So estimating A and B is like fitting a line through this cloud of points. And you see that as you add more and more observations at 0.7, that's not going to help you estimate A and B. Well, I'm out of time, so here are my conclusions. The size of the active management industry can be large even if the track record is poor. And in our mind, the first order mechanism here is decreasing returns to scale in aggregate. Learning about returns to scale is endogenous and slow. In fact, you never learn A and B exactly. And the model has some interesting features. Thank you.
Thank you, Bosch. Please visit us at www.agc.edu.